Okay, so this is the second video for week 2. My aim here is to walk you through what it takes to do a calculation for diatomic molecules. The WebMO tutorial is pretty good, but just in case, this is us doing it on exactly our systems and exactly using the spreadsheet that I'm suggesting you use. So I'm going to share my screen and go over here, and we are now sharing, and I'll check to make sure, but you should be able to see week 1 WebMO CS, and that's because we're doing a calculation on carbon sulfide. I am going to do a Hartree-Fock optimization plus vibrational frequency calculation. Once we've done that, I'll show you how to record the relevant data. We'll display the MOs and the molecule's electrostatic potential, so we get a sense of where the electrons are. And then we'll separately calculate the energies of carbon and sulfur so we can calculate the dissociation energy. Okay, so there we go. While we're at it, let's see if I can find it here. Let's just go to our shared Google Drive, Chem164 Fall 2020. You'll see it's got a whole bunch of weeks. Not surprisingly, we are on week 1. And if you go to week 1 assignment, you'll see that there is a file called sample diatomic data spreadsheet. You can open that. And then if you say file and make a copy, then you can call it something that is representative of your name. That way, that is, if you didn't do this, your data will go in that spreadsheet, and then other people will be annoyed because they'll have to remove your data. So if you make a copy, everything's good, but I'm going to go back and I'm going to use the RJC CS calculation. You'll see what we're going to do. I'm going to put in the molecule that I'm going to work on, and then a little bit I'll put in carbon and I'll put in sulfur, and the rest of it we'll fill in as we go along here. Very interesting doing this. My inclination was to say, everybody okay? Anybody have a question? But unfortunately that won't work for us here. So, okay, so what are we going to do? We need to call up WebMO. WebMO is the graphical user interface that is going to allow us to make molecules and to analyze them. And once you've done it once or twice, then when you call up in your browser something that starts with Gandalf, it may automatically log you in, and that's what it did here. Generally, what you'll see, if you haven't done it a lot, is you'll see something that looks like this, and you'll say log in once you put in your Harvey Mudd credentials, and there'll be a blank space here. So I'm going to say what I want to do is a new job. I want to create a new molecule, and I'm going to click here because I know that WebMO, like almost all quantum chemistry software, defaults to having carbon be the default atom that you're going to build with, because they think everybody's an organic chemist. And so now I'm going to put a sulfur out there. There it is. And I'm going to, it's probably a double bond or something like that. Now, there's a problem. Is that WebMO sees a carbon with a double bond and it says, well, it's missing 2 bonds. There should be 2 more bonds there. We really don't want that. So I'm going to define the hybridization here to see if I can beat that. So let's see if I can do, and now it's sp3. Let's see what happens if I say sp. Then I can hit clean. Bummer. It put 2 hydrogens on anyway. All right, well, so then I'm going to take those hydrogens off. I'll just do this, and that's good enough. If I want, I can check the charge on carbon, and it's 0. That's good. And I can check the charge, I can check the charge on sulfur, and that's 0 as well. So I've got a neutral CS here. And the bond length is some guess, but we won't worry about it. All right, so I built the thing that I want to test, this diatomic molecule. So now I go ahead and for our purposes in this class, almost always, we will use the Gaussian series of electronic structure theory codes. So that's what's highlighted there. I think probably when yours comes up, it'll say games, but you hit Gaussian. There's all sorts of queues you can submit to, but let it just be work queue for now. And now we're actually going to tell it what we want to do. So the first thing I've asked you to do is an optimize plus vibrational frequency calculation. I've asked you to do it at the Hartree-Fock level, and I've asked you to do it in the correlation consistent polarized valence double zeta basis. That's a mouthful, that's why it's abbreviated. I also said that you got to pay attention to what the ground state of your molecules is, but CS, like almost everything I think I put in your choices, is a ground state singlet. The way you think about this multiplicity for our purposes right now is the multiplicity is the number of unpaired electrons plus 1. So carbon sulfide has all doubly occupied orbitals. So there's no singly occupied orbitals. Plus 1 gives you 1 or a singlet. And of course, you can see there's all these other choices, and we'll see them when we get into atoms. There are other choices you can make here, but in fact, you don't need to do any of them for something as simple as a diatomic. We're just going to go ahead and do this. So I lost it by going back, and there's CCPVDZ. And then if you want it to run, you just hit this. And it'll sit here for a minute or two. This is probably a pretty fast calculation, but I'm not going to accelerate it because we could all do with catching our breath. Oh, but there it is, complete, 7 seconds. So let's see what happened here. So I now have CS again, and if I wanted to, you've all learned how to do this. You can figure out what the bond length is by clicking on that. So 1.526 angstroms, we'll come back to that. We have an overview of the results that came out. So here's the Hartree-Fock energy. The R stands for restricted, which means all doubly occupied orbitals. It's calculated vibrational frequencies, so it knows how to calculate a 0-point energy. It's calculated in internal energy at 298 degrees. So how energized are all the possible motions of the molecule. So that's rotation and translation. It's calculated in enthalpy, assumes it's gas phase, it adds PV on. And it's calculated in entropy and then calculated in Gibbs energy, which it names free energy. Here it has a heat capacity, there's the entropy, and we see the molecule as a dipole moment. All right, that's a summary. As we talked about in the previous video, the program has to take several steps in order to get to something close to the equilibrium geometry. So the first step has an energy like this. The second one, well, the energy went down a little, third, fourth, and then it's finally stabilized. Remember that these are in atomic units. So if you want to think about it, 1 atomic unit is 627.51 kilocalories per mole, or 2,625.5 kilojoules per mole. Chemistry occurs on the order of 100 kilocalories per mole, or 400 kilojoules per mole. So the numbers we care about really go out to this 5th decimal place. They're tenths of kilojoules per mole, right? So I know it's tempting to say, well, I'm going to take 3 decimal places, but none of these numbers differ in that regard. You really want to go out to 5 decimal places when you're thinking about these numbers. Lastly, it has calculated vibrational frequencies, so it might as well, it thinks, display for us what the modes look like. So if I hit this little animation, well, not surprising. What else could this thing do? It's just going to go back and forth like a harmonic oscillator. So I'll reset the viewer there. And now I want to collect the data that is relevant from this calculation using Hartree-Fock, PVDZ basis, opt plus frequency. So let's see what we got to get. Well, we want the job number. That's so I can go check on your stuff. It's not like I don't trust you. It's just that sometimes when people make a mistake, I have to go find it. So there it is, 5575. I'll put that in there. Theory, we did Hartree-Fock. Basis, we did CC-PVDZ. We did an opt plus vibe frequency calculation. The multiplicity was singlet. And now I got to get some energies. And so one could take this energy right here, the RHF energy, and you could try and type it in. And I guarantee 1 out of 3 times you'd make a mistake. So I'm going to use copy and paste. Copy it in there. And then I'm going to go get the Gibbs energy. which is right there. And I'll cut and paste it. And sadly, there is no way to cut and paste the bond length. That you actually just have to click on, and 1.526. So you just record that in here. In angstroms, and then lastly, the vibrational frequency, which is right here, 1. And these are in wave numbers. They're ridiculous, but spectroscopists like them, so we're stuck with them. All right, so that's that calculation right there. And you can't do much with it except to say that's the vibrational frequency and that's the bond length, but in a little bit, we'll do a bit more. Okay, let's take a little breather and ask what we're going to do next. The next thing we're going to do is actually just look at the molecular orbitals. And that tells us something about where charge is distributed. And the way we're going to do that is we're going to take this optimized geometry. So this is the minimum in the potential energy curve. So we'll say new job using this geometry. So what it's done now, if you wanted to check, oops, I don't want to do that, so I will undo adding that carbon. If you want to, you can go ahead and check what the bond length is, and it's exactly the equilibrium because we started from that, but it's not a bad thing to check. Okay, so I'm going to do a new calculation. I'm going to do Gaussian. But instead of opt plus vibrational frequency, I'm going to ask for molecular orbitals. And I'm going to run it again. And you see that in the list, it comes up and says, well, you're doing a calculation on cesium sulfide, carbon sulfide. But you're doing a molecular orbitals calculation, and there, this thing was even faster. It gave us those. And, you know, it's the same molecules, kind of looks boring there. But if you go down here and say show all, you can start to look at the molecular orbitals. So we'll view it. And it's a little hard to see that one. That one's a 1s on sulfur. But that one you can see. The reason you can't see the 1s on sulfur is that atom representation, the nucleus representation, is bigger than the orbital. But when you get to carbon, the 1s is a little bigger. You see a 2s on sulfur. You see a 2p. All three have the same orbital energy, so you know that they're equivalent orbitals. Here is, oh, the first one that's sort of spread over the molecule. So it's kind of a bonding orbital between carbon and sulfur. There's another orbital. It kind of looks, well, it's hard to know, right? It looks like 2s on the carbon, and it looks like an sp hybrid on the sulfur. There's another one. It's got bonding density that is no nodes between the carbon and the sulfur. And then we're going to see two pi-like orbitals. And you see that in both cases, those pi orbitals have more density, more space, more size on the sulfurs. So you have this sense that it's a little bit polar. We look at properties instead. We could look at the electron density, which is almost always boring. It's the sum of the squares of all the orbitals, and it kind of looks like a potato. But you could instead look at the electrostatic potential. And that's kind of interesting because, let's see if I can get it to stop moving around. Because what you see is that there's sort of a red end out here where the carbon is, and a bluish end here where the sulfur is. Kind of looks like the molecule has a negative positive dipole moment. Let's just see if there's anything else we could see that's interesting. Probably not. Let's go back to electron density just for a second. One of the reasons that you might be surprised that the carbon looks kind of negative and the sulfur looks kind of positive in electrostatic, that is you think about electronegativities. But you know, the dipole moment is charge times distance. And if you look, there's a lot of negative charge sticking way out here like this. And it turns out charge times distance, this is the same thing that makes this carbon monoxide have a negative end be the carbon. So it's kind of interesting to me. All right, so now you've seen orbitals, you've seen electrostatic potential, and there wasn't really anything to record in that. I didn't ask you to put down a dipole moment or anything. You could have, but for right now, all we're going to do is we're going to go get atom energies for carbon and sulfur. So the way we're going to do that is we are going to reset the viewer. We're going to go job manager. We're actually going to say we want a new job. And the new job is just going to have a carbon atom there because that's all the energy I want, or it's the only part of the system I want. We'll say carbon, and there's no optimization to do for carbon, right? There's no bond lengths to change. So we'll just get the energy. No, it's not a molecule, but as I said in the notes, WebMO sort of defaults to you must be doing molecules. The charge is 0, but here multiplicity is an issue. If you think about a Lewis structure, well, no, you don't want to think about Lewis structure. You want to think about it at an AO diagram for carbon. Carbon has 6 electrons. It's got a 1s squared, 2s squared, 2p2. And those p's all have the same energy. And one way or another, but we can prove it by doing a calculation, we know that it is lower energy to have electrons in separate orbitals, if they're in degenerate orbitals, and have their spins aligned. And that means that carbon's ground state should be a triplet. And if you don't believe me, you are welcome to do carbon as a singlet and see which has the lower energy. In the meantime, we'll do sulfur. And sulfur is just like oxygen. It's, in this case, it's 3s squared, 3p4. It means it's 4 electrons in the degenerate 3p orbitals, which means that I could pair them all up, get a singlet, or I could have 2 electrons in a doubly occupied orbital, 2 singly occupied orbitals. And Hund's rules, or whatever you like, would tell you that that's exactly what should be there, that sulfur should be a triplet as well. So I did that calculation, or I'm doing that calculation. Carbon finished, so let's go look at that. Not much to it. There is just an energy here. Unrestricted Hartree-Fock UHF just means that there are unpaired electrons. So I will go in here and I will put the energy of that carbon atom right there. This was job, well, let's find out what the job was. It was job 5578. And all the rest, those two are the same. It is a triplet. It is an energy. And all of this will be true. Triplet, not tiplet. All of this will be true for sulfur. And let's call that one up. Manager, sulfur, 5579. And its energy was this. Okay, so this first assignment, what are you asked to do? You're asked to calculate an equilibrium bond length, the vibrational frequency. You're asked to calculate the dissociation energy of your molecule, which is the energy of the molecule minus the energy of the atoms with a minus sign to get it positive. We've done it all. So that doesn't mean this is trivial. It just means that I feel confident you folks can make a stab at it. We'll see what happens. And that's all we got.